This is a diagram of the particle accelerator I worked with at Macalester College. I think it was 150,000 volts. So I think we did proton-induced X-ray emission, PIXI. I can't remember. We did some other experiments, but basically the idea is that we accelerate ions through a vacuum. So there's some difference in potential. In this case, V is 150,000 volts, right? Q is, of course, the electron charge, right? And then that becomes the kinetic energy, right? And at low velocities, I don't even think this velocity would be valid. You can calculate the velocity using this formula, right? Okay. But basically, the idea behind a particle accelerator is to provide energy for nuclear reactions or to create particles, right? If two protons hit head on, okay, they can actually create a panoply of particles that are very short-lived, right? So notice how we've got these masses in millions of electron volts. We talk about particle energies in millions of electron volts. And if you take a look at the list of particles here, we've got electrons are stable, right? We've got protons are stable, okay? Bound neutrons, by the way, are stable, but all the rest of these have exceedingly short lifespans, right? And so if we want to study these particles, we have to create them in a particle accelerator. Now, these particles were once abundant, like right after the Big Bang. It was a seething mess of all these particles, but these don't get spontaneously generated by open space anymore, not very often, right? Okay, so in that way, a particle accelerator is a bit like a time machine. We're getting back to higher energies because the universe started out very hot, very energetic, and particle accelerators are a way to get close to that. So it's one, physicists have two time machines. The first one's a telescope, of course. If you look at something that's 1 billion light years away, you're seeing it 1 billion years ago, right? And the other one is a particle accelerator. We can look at the way the universe was when it was hotter, okay? A lot hotter, okay? Here are some interesting particle accelerators. So basically, my particle accelerator at Macalester was a single stage. You just accelerated through 150,000 volts once, okay? Check this one out. This is a multi-stage one, right? So this is an electron that they're accelerating. It accelerates toward this because there's some huge potential difference, and so it accelerates through that. When the electron is inside the cage, we change all these. So this becomes plus, this becomes minus, this becomes plus, this becomes minus. And now the electron, as it passes through here, accelerates across that gap because it says, oh, yippee skippy, here's another positive voltage. Remember, there's no electric field inside of a conductor. So inside that tube, it doesn't know we've changed the potential, right? So it accelerates through that potential again, boom, right? And while it's inside this tube, we change the potential again. So now this is positive, this guy's negative, this guy's positive, right? And the electron accelerates across that gap. It'll accelerate across this gap, across this gap. Notice how it's getting longer and longer. The segments get longer and longer, and that's because it's going faster and faster. And it's all cleverly figured out. They figure out exactly what rate to switch the potential. I think it's like 2 miles long or something like that. Here's a picture of it from the air. I think that's Highway 280. It goes under Highway 280, which is sort of funny. Okay. And it achieves a mass of, an energy of 50 giga electron volts. Okay. And that's an interesting thing too. At Macalester, okay, we had 150,000 volts, right? Okay. Well, that is another way to write 150,000 volts is that it's 0.150 MeV, right? Okay, 150,000. 1,000 is 150 keV, right? It's 0.15 MeV. Well, the mass of an electron is 0.511 MeV. And the thing you got to know about electrons and any particle in general is as you give it kinetic energy, right? Okay, it gains mass. So this electron in Macalester College, ordinary electrons, when they had been accelerated through that potential, had a mass of 0.661 MeV, okay? Because we added this energy to it. And remember, energy is mass, right? Okay? And so if a 0.150 MeV electron actually has this much mass. And you can tell that it has that much mass. When you put it in a magnetic field, it has a longer radius of curvature, and we can measure it that way. So mass dilation, relativistic mass dilation, isn't pie in the sky. It's something we measure. It's ultimately what limits what the energies we can get in these particle accelerators. And then here, this is a cyclotron. And a cyclotron does the same thing that SLAC does, okay? Except that it's not linear, it does it in a circle. So basically we've added the idea that we put it in a magnetic field, right? And so the magnetic field, we understand, these are supposed to be magnetic field into the page, right? I think this guy is accelerating protons is my guess. Let's just see, magnetic field, yeah, okay. Yeah, this is definitely accelerating protons. And every time it gets to a gap here, okay, it's going to accelerate across this gap. And so we basically, when the proton is going this way, okay, we make sure that this side's positive, this side's negative, and it accelerates across that gap. Whilst the proton is traversing this path here, we switch the polarity. That's what this little squiggle sign means, right? So that this side's positive, this side's negative. Every time that proton reaches that gap, it always has a negative in front of it and a positive behind it, and it accelerates across that gap. Now, because it's accelerating, it spirals to the outside because it's going faster and faster, and eventually it exits the side here, okay? A synchrotron is just a fancy cyclotron. Synchrotrons take packets of protons and speed them up, and it has to, because the mass is dilating, it has to actually change the frequency with which it does that, and it does it cleverly so that every time a packet of protons reaches the gap, it accelerates across. Fermilab is a synchrotron, I think. The superproton synchrotron at CERN is a synchrotron, okay? And it feeds the Large Hadron Collider. It's one of the things that feeds it, right? Here's a diagram of the complex at CERN, and here's the superproton synchrotron, I think is the name of the SPS, right? The big ring here, the one that accelerates it up to super high energies, okay? That big ring actually uses little cavities and they have radio frequency. They call it RF, right? And as these packets of protons fly through these little cavities like that, they've got specially tuned radio frequencies that boost it along. It's a little bit like surfing, like a surfer surfing off of a wave. And every time it goes through, it boosts it up to a higher speed. Of course, all of these things have to operate in a super high vacuum. We've got superconducting magnets all along this track that are making these things go in a circle. And that's ultimately what I think what limits our energy is the strength of those superconducting magnets. You can't, at some point, superconducting magnets quit superconducting, and you can't. So there's a limit to the magnetic field you can make with them. Okay, this is a picture of CERN. If you could see underground. It's in a tunnel underground. This is Switzerland. Okay, that's where Atlas is in CERN. Here's a picture of inside the tunnels. Right, it's a giant curving tunnel. 27 kilometers in circumference or something like that. You could figure it out. 8.5 in diameter. This is a picture of the detectors. So what they do is they'll collide. It's a Large Hadron Collider, right? So it's the largest hadrons we have that are stable are protons, right? So we collide two protons together. And journalists like to say that accelerators smash atoms or something like that, and they look at the pieces that come out. It's actually much more exciting than that, okay? These things have so much energy that basically it's creating these giant jets of exotic particles. Some of them are just protons and neutrons and stuff like that, and pions and whatever, right? But every now and then it'll make something like the Peter Higgs boson, right? Okay, and all of these things here. We've got a magnetic fields here, so we can tell the charge these things have and their momentum from their curvature, right? Ultimately, we can figure out the mass of the particle, its velocity through these things. And basically what they do is they just gather tons and tons and tons of data. And they have sort of low-level stuff that sits there and throws out, okay, that's a boring thing. We've seen that before. It gathers the interesting interactions and does statistical analysis on those. And ultimately, there's some, some range. Like it's got to be the odds that it would happen randomly have to be 1 in a billion, or it's even more than that, right? So they gather tons of data and they do statistics on it to show that we've created some exotic particle. So it's not that we're smashing protons up to find out what's inside them. It's that we smash protons together and briefly an elephant appears, right? And the elephant, we know that the elephant appears because an elephant is the only thing that decays into 2 zebras, 5 horses, and 3 great whales, or something like that, right? Okay, that's my analogy, right? Is we know that, okay. Anyway, and this is a picture of Peter Higgs, and I think this is the Atlas detector, the detector for the Atlas project, yeah, that was, I think, 2012, right? Was when they confirmed the existence of the Higgs boson that we sort of knew would exist, right? Anyway, I think that's all I have to say about particle accelerators.